Okie doke, next video on non-renewables. And as you know, we're building on our workhorse. We're going actually back to a kind of DHSS structure, and we're looking at these three cases. We just looked at the sort of wind. Now we're going to look at coal, and shortly we're going to look at oil. Okay, so let's see. That was wind. Now coal. Okay, so what have we got here? Here we've got, okay, I've done this slightly differently, but whatever. We've got labor coming into the final goods sector. We've got final good coming out with the help of capital and coal inputs. Out of that final good, we can think of it as hammers, if you like. Some of it is getting invested in the capital sector, and then that stock of capital is used in production. I've sorted this picture out now. The rest of it carries on. Some of that goes as inputs into the coal sector. Some of it goes to consumption. So effectively, these inputs, it's in a way we're going back to Farzin here. But we have to bear in mind, we have to think of these inputs as a bit like embodied capital and labor and coal. So we've used capital, labor and coal to make this final good, which we're then recycling as an intermediate to extract more coal. So effectively we're using capital, labor and coal to extract coal. So then we have to bear in mind that the technological progress in labor productivity is sort of embodied in this input. Okay. Right. And then this is an abundant resource, costly to extract. Okay. So we're saying the stocks are infinite and the cost of extraction, or the quantity extracted per unit of input, is just constant. Okay, so it doesn't get harder to extract over time. There's plenty of it near the surface. You might say, well, surely coal is going to run out at some point. To which I would respond, I certainly hope it doesn't, because if we add climate change to this model in the background, we know that we have to stop using coal way before it starts running out. And then if you look at coal extraction in, like, is it Virginia, I think, in the US, in Australia, we are still scratching the surface. We're just lifting coal off the surface pretty much. Okay, so this makes a fair bit of sense, this assumption. The extraction costs today aren't higher than they were before, or the difficulty, the coal that we're extracting is not harder to extract today than it was 100 years ago. In fact, it's probably easier because 100 years ago we were in deep mines. People were going down deep mines in the UK because we didn't know any better, kind of. Okay, so that's the model. How do we solve it? It's actually pretty straightforward. I'm wondering whether I even want to take you through it, but I think I will. You don't have to watch this, but you should be able to do this super easily yourselves. Okay, so, but I'm going to kill this window and I'm going to take you through it. So let's see if I can do this. So what have we got? We've got, again, it's similar to last time, right? We've got y is ALL 1 minus alpha minus beta k to the alpha r to the beta, and we've got k dot is s y minus x minus delta k. And we're not interested in the case where capital, there's just been some earthquake or something and capital is out of kilter. We're interested in the case where the capital stock is in balance with the technology, which is growing, of course, which is there's technological progress in the background. So we're interested in the balanced growth path. Okay, and on the balanced growth path, we know that state variables such as k grow at constant rates, which might be 0, right? That's also growth at a constant rate, by the way. So we can divide through by k, and we say s y minus x over k minus delta. So if this is constant, this all has to be constant. And s is constant by assumption, delta is constant by assumption. So one way to make this constant is, of course, to make y, x, and k all grow at the same rates. You might imagine in the short run, it might be possible for y to grow. If k is growing at some rate, y could grow faster and x could grow slower or something. Faster as well, I guess. Yeah, because then it's minus and it could still work, right? But in the long run, that is never going to be a long run balanced growth path, okay? Because you're going to end up sort of unbalanced. I'm not going to prove that. We could prove it, but I'm not going to. Okay. So basically, a little bit taking on trust, this shows that all of these have to be equal. Okay, on balanced growth. And then we do the differentiation with respect to time. Remember, we need to go like dy dt is dy dal dt plus dy dl dt, dy dk dt, dy dr dt. And quickly that tells us L is constant, AL dot over AL is just G. We end up with 1 minus alpha minus beta times G plus alpha K dot over K plus beta R dot over R. And then from this, we know that we get the same result as before, of course, because the equations are the same. We get y dot over y is 1, let me see, 1 minus beta over 1 minus alpha G plus beta over 1 minus alpha R dot over R. But wait a minute, because we know that R is just phi x, the extraction rate is just a linear function of the inputs. So R dot over R is also x dot over x, which we know from before is y dot over y. So actually, yeah, I should have done this in one step, right? I should have, we can scrub this line and we can say, look, this is also y dot over y. So it's alpha y dot over y plus beta y dot over y. So we end up with y dot over y is g. So in this case, on the balanced growth path, you get growth at the rate of technological progress, g. In the previous case, where this flow was fixed and couldn't grow, you got a slightly lower growth rate. Okay. as long as beta is greater than 0, the fact that this can't grow along with capital and along with labor productivity slows down growth a bit. But now this can grow along with capital and along with labor productivity, and y grows at the full growth rate, so to speak, g. Okay? And what happens to the quantity of resources extracted? That also grows at g. And I can't remember, I don't think we've got those pictures here. No, we haven't. But if you remember the let's see if I can do this. If you remember the picture I showed you before with like 100-year time series here and a log scale here, and we had y growing like that, and then we had quantity, it's like we had r growing like that, didn't we? And that was like for aggregate metals, and it was also for aggregate primary energy. And then the price basically did this, which is also, of course, what we're going to see in this model, because we have this r equals phi x, the unit extraction costs are just constant. Okay, because the cost of x, what's the price of x? It's normalized to 1. So we've got, these are the inputs, this is the flow of output from the mine. The price of the input is constant, so clearly we've got constant unit extraction costs. What's the price going to be? It's going to be 1 over phi, isn't it? Or is it going to be phi? I have to slow down and think. I think it's going to be 1 over phi, right? Okay, so this version of the model fits reasonably well for things like coal. Okay, and I think that's that for this video.